When you upload documents to an AI service, you're placing a lot of trust in that company. Trust that they'll keep those documents secure, that they won't use them to train their models, and that they won't end up being exposed in a data breach down the road. And for a lot of documents that's fine, but for sensitive ones, like legal, medical, financial, or client docs, that's a much bigger ask. For these you need full control. So today we're going fully local and air-gapped. No external APIs. We're going to build an AI agent in N8N that can interrogate your private documents using a technique called RAG, and all running fully privately on your machine and available to others in your local network. And in many ways, this is the future of AI in business, with local models getting more and more advanced, and companies looking to reduce risk by deploying on-prem. The stack we'll be using today includes N8N, Ollama, Docling, and Docker. And while all of that might sound complicated, there's no need to worry because we're going to build everything out step by step, so by all means follow along, and soon you'll have your very own local multimodal RAG agent up and running. Alright, let's get into it. So what do I mean by multimodal RAG? Well, here I'm talking about retrieval across a knowledge base that has multiple data types. So we could have text documents or PDFs with embedded images or tables. We could have audio files like meeting transcripts or even videos. And the benefit of multimodal RAG is that when you process a PDF that has an embedded image, for example, then that embedded image can be retrieved and returned as part of the chat conversation with the agent. So this is incredibly powerful because a lot of AI agents will only ever return text from your knowledge base. So what's the best way to process all of your files locally and make them accessible to your agent? Well, this is where we use Docling, which is an open source document processing library created by IBM. With Docling, you feed it PDFs, Word docs, PowerPoint presentations, images, audio files, and it spits out clean, structured Markdown or JSON that your agent can then search over. And this isn't just basic text extraction. Here, as you can see, it's able to recognize headers, it's able to recognize tables, it can extract these diagrams as images, and the text in the diagrams is actually searchable as well. So you are maintaining the semantic structure of the document. Here we have bullet points, for example. And under the hood, there are two distinct ways you can actually process documents. The first is using their standard pipeline, which is a pipeline of specialized models and algorithms to analyze layout, extract out table structure, carry out OCR, and then assemble the output to be exported into a different format. And the beauty of this approach is that even though there are AI models involved here, they're non-generative models. So you don't end up with hallucinations. It is copying the text out verbatim. And there are specialized pipelines for different file formats. So for docx or PowerPoint, it knows how to parse those markup formats to actually create this Docling document, which you can then export to Markdown or JSON or XML, for example. There is also a different approach you can take with Docling, which is to use a VLM, which is a vision language model, similar to a large language model. With the VLM pipeline, it takes a document, which could be a 100-page PDF, for example, breaks it into pages, and then it batch processes those pages, sending each one into a VLM. And here you're asking the VLM to extract out all of the text as accurately as possible into a specific format like Markdown. And from there, the Docling document, which is the core of the Docling library, is created, and then it can be exported to lots of different formats. And VLMs can be quite powerful, but because you are dealing with a generative AI, you can end up with hallucinations in the extracted text. And in a way, that needs to be balanced with inaccuracies in OCR from the standard pipeline. So there is no 100% best approach, but I do like the standard pipeline for a lot of use cases. When it comes to VLMs, there are various options. So to run a fully air-gapped local system, you would need to use the likes of IBM's Granite Docling, Small Docling, or QuenVL. There are lots of cloud-based proprietary VLMs like Gemini, OpenAI, and Claude, but it's not possible to run any of those fully locally. And if you are looking at locally hosted VLMs, just go to Ollama.com, click on Models and Vision, and you'll see that there's a long list that you can actually use. Ministral from Mistral, DeepSeek OCR, so you have plenty of options. But then all of that leads to the hardware requirements that are needed to actually run local AI. Because these LLMs, VLMs, embedding models, all are based off a neural network, which requires billions or even trillions of parameters to be loaded into memory to actually output responses. And these computations are far beyond the capabilities of traditional CPUs and RAM. You essentially need a graphics card to actually run these. And within the system that we'll be going through today, we will be using a local LLM like GPT OSS 20 billion. We may want to use a VLM to ingest documents. There are the non-Gen AI models within that standard pipeline for Docling. And then we have embedding models to create the vectors that we can search over. So graphics cards are essential here. And there are various options that you can use. NVIDIA GeForce RTX cards are pretty common for local AI, but there is a limitation on the complexity of models that you can actually run on these. And the same with AMD Radeon and Apple Silicon. And probably the max size LLM that you can run on these cards comfortably would be in the region of 25 to 35 billion parameters. It is possible to load in larger models like a 70 billion parameter model, but you would need to heavily quantize it, at which point you're losing a lot of the quality of the model. This really is a key requirement if you are deploying local AI in a business. There is an upfront investment needed to build out the server to actually host this system. And the more concurrent users you have, the more hardware you'll need to actually run it. And tokens per second is critical here because people are used to the speed of response from the likes of ChatGPT or Claude. So there will be an expectation that a local system should be able to do the same thing, whether that's a reasonable expectation or not. An NVIDIA RTX 4090 is coming in at around $1,600. The 5090 is at the $2,000 mark. And from here, you'd need to build out a server further, but you can see that this is the fixed cost up front. And the benefit then is you have your fully local system and there are no cloud fees required to actually run it. An important thing to note is you don't need this hardware in place right now to actually build out your local AI application. This is what you need when you actually use this in production to air gap the actual system. But to actually set up and design and test your system with dummy data, you could use cloud-based open source models using the likes of Ollama Cloud or OpenRouter, which has lots of different open source models available to use. So at least with this approach, you can get started straight away, building out your solution, and then in parallel, you can actually start getting the infrastructure ready to go for when your system is going to be running in production. If you'd like to get access to our state-of-the-art local RAG system, then check out the link in the description to our community, the AI Automators, where you can join hundreds of fellow builders all looking to create production-grade RAG agents. Docling is an open-source MIT licensed application that's available on GitHub. And there are two particular projects to note. So there's the core project, which you can see on screen, and then there's also Docling Serve. This is an API wrapper on the core Docling library. And this is crucial because we want to use N8N as an orchestrator for our RAG pipeline to push in documents to be processed. So where do we go from here? We obviously want to set up Docling and N8N locally. So N8N has produced a self-hosted AI starter kit, which bundles N8N, Ollama, Quadrant, and Postgres together in a Docker Compose file. So this makes it quite straightforward to spin all of this up on your machine. The only thing that's missing though is Docling. So what I've done is I've forked this starter kit repo and I've added in the Docling Docker Compose into the starter kit. I'll leave a link for this in the description below so that you can follow along. But before we set this up, let's just take a helicopter view of how all of this actually operates. So all of these services are going to be running in Docker containers. And if you haven't heard of Docker before, Docker lets you run applications in isolated environments and isolated containers. And if you think about the applications we need to run locally for the system, N8N, Docling, Quadrant, they all have different system requirements, different libraries, they're written in different programming languages. So normally to get all of these applications running natively on your machine can be a bit of a nightmare. And thankfully Docker sidesteps all of that. So each application runs in its own isolated environment. And that way they can't conflict with each other because they can't see each other's internals. They just communicate over a shared network. And quickly, some terminology for you to understand. So we have Docker images, and these are essentially static. They pull in the application code, they define the environment for the application to run, but as I said, they're static. So to actually access those applications, you need to run them within containers. And that is a running instance of the static image. And the thing about these containers is that they're stateless. So when you create a container, let's say of N8N, it spins it up from this static image. And when you remove a container, it's essentially destroyed. And any information that was created in it is lost. And this is why you need Docker volumes or bind mounts. So this is a way of persisting or saving the data long term. So from an N8N perspective, if you were creating workflows in a running instance of N8N, you would want to save those workflows to a volume or to a bind mount. That way, when the Docker container is deleted, you haven't lost the workflow, and you can simply spin up the container again from the static image, and it'll load in everything that's available in the bind mount or in the volume. So these are the three crucial concepts you need to understand about Docker. And then when it comes to the Docker network, as I mentioned, they're isolated containers, so they can't see the internals of each other's containers. So they need to communicate over a network. And this trips up a lot of people that aren't used to Docker. So if you have N8N as a container, and it's trying to speak to Quadrant or to Docling, it needs to communicate over the Docker service name. So it would be Quadrant and then the port, or Docling and then the port. Whereas if you're trying to access N8N, you would just use localhost and then the port. This will make more sense when we actually start building out our workflow. But what's important to understand is this idea of the Docker compose file, because here we're orchestrating the creation of multiple services, and we're defining these volumes, the persistent layer, we're defining the ports, as well as other things like environmental variables. If you haven't used Docker before, I highly recommend you install Docker Desktop, which is a visual interface into the volumes, the images, and the containers. And finally, if you're new to building and deploying local AI systems, then you should definitely use an AI code editor. These things give you superpowers, and they're brilliant for troubleshooting issues with Docker Compose files or networks. They can provide the prompts that you need to use to actually spin up containers, to help you version control your system. The list is endless. So for this project, I'll be using Cursor, and that's where I'm going to start. If you're enjoying the video, make sure to give it a like below and subscribe to our channel for more deep AI and N8N content. It really helps us out. So open up Cursor. Again, you can also use VS Code or anti-gravity. And I'm just going to click clone repo. And I'll grab the URL of our forked AI starter kit repo. And we'll just select as the repo destination. And then it starts cloning in the repository. And here we go. We can see all the files of the starter kit on the left. We can see the Docker Compose file that I talked about, and that includes the definitions of all of the services that needs to be spun up. So if we go back to the repo, there's full instructions on what commands you need to trigger. So we've already cloned the repository, and here it's asking to change directory into the starter kit. We're already in it here. Now we just need to copy the environmental variables. So we can copy that out. Now you could just copy and paste it here, Control-C, Control-V like that, and rename it. So that works. Or based off the terminal commands, we can open up terminal here with Control-J, and then you can just paste the command into there and click enter, and that also copies it. So either works. So we need to set some encryption keys and passwords in this environmental variables document. There is of course lots of ways to generate passwords. I have OpenSSL installed in my Git bash here. So I'm just going to generate a 32 character key. So that looks good. So that could be my Postgres password. I might just get rid of the equals at the end. And yeah, I'll just generate a couple more. That could be my N8N encryption key. Again, I'll remove special characters just in case. And then back to the instructions. So I am on an NVIDIA GPU here. So I can now run this Docker Compose up command, passing the profile GPU NVIDIA. But obviously if you're on AMD or Apple Silicon, you have other profiles that you can use. So I'll just copy that out and then back into here. We'll paste it in. And what that does is it downloads the different images that are needed to actually run the system. So we're bringing in N8N, it's downloading Postgres, Quadrant is already imported. And this can take quite a while. Docling in particular has some pretty heavyweight models, so you're talking about a number of gigabytes. If you're on a slow internet connection, it'll take even longer again. But eventually all of your images will be downloaded, and then it can start spinning up the containers, as you see here. We can see that we have our self-hosted AI starter kit, and if we open it out, you can see Docling, N8N, Ollama, Quadrant, and Postgres. Now there's also one other container called static files. I'll talk about that in a second. And within ports here then, you can see different ports. So if you click on the first one, which is Docling, which is port 5001, and that opens up localhost port 5001. Now it says details not found, but if you just add in /UI, you now have your Docling serve application. And the same goes for the rest. So for N8N, if you click that link, you have 5678 and you're brought to the setup page. For Quadrant, it's 6333. And if you add /dashboard, it'll bring you to the dashboard. So this is your vector store. I don't believe we have a UI on Postgres, but that's fine. We could hit that with a database client. And then we are serving static files on port 8080. And this is how the multimodal RAG aspect is going to kick in, because the images we extract from PDFs and Word documents will be hosted here and available within our chat. So we can see this is now up and running. So if you click on the actual group, you're able to see a stream of all of the logs from the different services. And if you want to see log files from any particular service, just click into it. So Docling, for example, you can see that there's a lot of health checks going on. This is how it started, and it's given links to the likes of the docs. So if you click on that, it's bringing us to a site can't be found, but that's fine. We just need to add in localhost instead of 0000. Okay, so there's our Docling API docs. So that's how you can track the logs for the different applications. And that is important if you're trying to troubleshoot or debug a problem. So let's start with N8N on port 5678. So here we need to set up an owner account. Now this is all local. This is not N8N Cloud. You just need to create an account to be able to log in. And that brings us straight into the list of workflows. And there is a demo workflow that's auto-loaded by the N8N starter package. And it has Ollama chat configured. So we'll get back to that in a second. What I might do quickly though is let's just go into settings. We just need to enter an activation key because there are certain features that are gated, such as the idea of pinning previous executions, which is really important when you're building out workflows. So if you click on unlock on the top left here, then you can just enter in your email address and they will send you the activation key. This is totally free and everything is still local. Okay, so that has been activated. So now let's create a workflow. And as a first step, let's add a local drive trigger. So we'll come in here. Let me just move that out of the way. And under other ways at the bottom, we can see local file. So we want to trigger changes that involve a specific folder. So here now we're going to start building out our RAG ingestion pipeline. So we'll click on that. And at this point now we want to watch a folder to find files as they're dropped in. That way we can drop in a file, 10 files, 100, 1,000 files, and have them all processed. So we need to add in a folder to watch. And this gets back to the volumes and bind mounts because this needs to be a persistent folder. We don't want this to be destroyed when we delete the container. And within the README file for the repo, you can see that they provide the path data shared as the path to use. So if we drop that in there, and then we're going to execute that step, and let's see, can we trigger the files? Now, actually, there's one change I need to make. So we'll just stop listening. We need to use polling. So for whatever reason on my local system, this doesn't work if I don't use polling. So we'll just execute that step. And if we come back into cursor and let's go to the Docker compose, just to explain what's actually happening here. Under the N8N service, you can see that we have volumes specified and we have a bind mount. So you can see that the shared directory, which equates to this directory here, is mapped to data shared, which is what we just entered into N8N within the container. So now if I create a file here, so let's just add in a file, let's create a new one, test.txt. And as you can see, that has just appeared, data shared test.txt. Now there's nothing in it, but just to prove that it works. So okay, let's delete that. And within our version of the Docker Compose, I've created a folder called RAG files. So that way we can drop all of the files we want to process into here. So under RAG files, let's create a new folder called pending. And actually, let's create another folder called processed as well. That way we can ingest a file and then move it to the processed folder. So now let's just update our trigger in N8N. So we're now looking for files that are added to the shared RAG files pending path. So data shared, RAG files, pending, and let's execute that again. And now let's get a PDF that we can actually start processing. And let's use the one that I demonstrated in the intro, which is this Whirlpool refrigerator spec sheet. It's only one page, so it's a good test bed to build out the pipeline. So I have my pending folder here. So let's just drag in this PDF into that folder. And as you can see, because I had this local file trigger executed, it was waiting for a file to appear and it has just done so. There we go. So then a good trick at this point is just to pin that data. So just click P on the node. And that way now if we click execute workflow, we don't need to keep dragging that file into that folder. That data is always there. So next up, let's actually load up this file. So if we click on the plus and just type in read, we're going to read this file from the disk, which is that one here. And now we need to provide the path for this file. So that's the path there. We just drag it in. And now if we click execute step, there's the binary file. And you can see by opening it up, that's it. So we now have the file to actually play with. So next up, we need to send this to Docling to actually extract out structured information, be it Markdown or JSON. So if we go back to Docker Compose, we can see Docling is on port 5001. So if we click that, and again, if you go /UI, you can see Docling serves own interface. But we want to access the API documentation. So that's done via /docs. So then we just need to figure out what API we need to hit. So we're looking to convert this file. We want to process the file. Now there's two options. You can either asynchronously process a file or synchronously process it. So I'll show both. So let's just do synchronous processing. In other words, we're going to wait for the response. And you can see on the top right, this is the path that we need to hit. So let's just copy that, bring it in here, and let's use a HTTP request node. And we're going to post to this endpoint. Now you'll see this is mentioning localhost, which is incorrect. And I'll show you why in a second. But essentially we want to pass this file to this endpoint. And in terms of the body to send, we're going to send the binary file. So that's done using either N8N binary file, or you can also use form data, which is what I'm going to use. And if we go back to the documentation, you'll see that this requires a parameter called files, and that's an array of binary files. So we'll just copy that and let's drop it in here. And the value is data. And let's leave it like that for the moment. So let's save that. And now if we execute the workflow, we're going to hit an error, which is to be expected. And it's saying the service refused the connection. And the problem is this local host. And if we come back to our Docker network diagram here, what's happening is this N8N container is trying to communicate with Docling, but it's using localhost. And localhost is limited to the machine or to the container. So when it's trying to hit localhost 5001, it's actually searching within this container. So we need to hit Docling port 5001. And that way it's actually looking at the broader Docker network to pass the file. So we'll just change this out for Docling and then click execute step. And now we get a different error, which is great. We're making progress. And it's saying the request is invalid. And the issue here is I'm passing a string as opposed to a file. So it's just this parameter type. We just need to change this to N8N binary file. And then, yeah, put that back in as data. And let's execute it again. And there we go. It's thinking about it. Okay, we do have a response. And the fact that it was thinking about it meant that it actually processed the file. So that's why there's two different endpoints. There's the synchronous endpoint where you wait for the response. Or if I put in async here, it'll just give me back a task ID and then I can poll for the result. But let's leave that off for a second. And if you have a look at the data here, there's a lot of kind of image data. This is base 64 image data. And then at the end, we do have the actual text from the document. So if you go through the API documentation, you can see that there are different parameters that you can pass. And Docling is quite comprehensive and flexible with the API endpoint. So image export mode is the next one. So let's actually just drop that in here. We'll add a parameter. This one is now text, not the binary file. And then if you choose placeholder, for example, and then if you execute it again, now you'll see the document has been processed. And where there are images, it just says image, but it is just a placeholder. You've actually lost the image. It hasn't extracted it. So instead, let's use referenced, because what that's going to do is it's going to save that image, as you can see here, to the disk. So we have the actual image name now. And if we go to cursor, on the left-hand side here, we have a folder called Docling Scratch. And if we open that up, you can see all of the images that were just extracted from that PDF. And that's what that referenced flag does. It, instead of providing the image as a base 64 string, it saves it to the container. And this is all made possible by the way I set up the Docker Compose file. Under the Docling configuration, I've set the working directory as this shared folder, and I've also set it in various environmental variables. And because this shared folder is accessible to both Docling and N8N, it's now possible for N8N to actually pick up those files and move them somewhere else so that we could serve them as part of a chat response. Which then brings me to this static files container that I set up here. So in Docker Compose, this is essentially just a really simple Nginx server that makes a particular folder available. And as you can see, that's on port 8080. So if we click into the actual port here, you can see we have Docling Scratch at the RAG files. So let's create an extracted images folder, and then we can dump all of the images in there. So we'll come back in here, and under shared, we'll create a new folder, extracted images. And now if we come back here and refresh, we can see extracted images. So we probably should lock this Nginx server down to this folder. So under the volume, we can see that shared is actually accessible. So let's just lock this down further. So yeah, it's now shared extracted images. And now all I'm going to do is delete this static files container and recreate it, and it'll build it back up again off the back of the server configuration. So this is the beauty of Docker. So we'll come in here, static files, and delete. And now we just need to rebuild this image. And down here, you can see actually that we're still getting logs of the various services that are running. So we need to run this in detached mode. So if you just press Control Z, that'll stop all of the containers. And now we'll just make one change. So if you press up, you're going to get the previous command that you ran. And now we're just going to do /D, and it'll run it in detached mode in the background. So just press enter, and that's going to re-up all the containers. And it's also going to rebuild that file server container with the new configuration. Okay, so now if we go back to the index and if we refresh, cool. So there's nothing now in that folder. We are also locked down to that folder as well. Okay, so let's go back into N8N. Let's just refresh it. And as you can see, our workflow is still here, even though we just removed all the containers and added them again because we have a dedicated N8N volume. Okay, so let's just run this again now. And the document has been processed again. We can see the markdown content. We can see the image names. And if we go to cursor under Docling Scratch, we can see the images themselves. So next up, let's move these images into this extracted images folder. And that way they'll be able to be served in our AI agent chat. So we essentially need to extract out all of these images. So as usual with N8N, there's lots of different ways you can go about this. What I'm going to do is I'm just going to copy this entire output. So copy selection. And I have cursor here with Opus 4.5 set. So I can literally just ask cursor to do this job for me to create a code node to extract out an array of image names. So I'm saying, can you create JavaScript code to extract out an array of image names? And I'm saying, here's my JSON input structure. So I'll just copy that in. And then I'm also saying, here's the skeleton of the code node for you to start with. So this is important. So here, let's just add our code node. We're going to use JavaScript and just copy this out. Now, you don't necessarily need this actual addition of a new field, so you can delete that. But yeah, copy that out and let's paste that into here. And I'll just say, just output in chat, no need to create a file, and off it goes. And this is key because the AI needs to understand the incoming data structure as well as the skeleton of the code node, because it might not understand this is N8N or the structure of the input items in N8N. So copying in the code node is a really good hack. Okay, so it's produced the code. So let's copy that. Let's paste it in here. And actually, before we run it, let's just pin this as well so we don't need to keep triggering Docling. And then let's execute the step. Yeah, there we go, image names. That's exactly what we want. So now we can split out this array. So let's do that quickly. Split out, and let's pass in our image names array, and we can execute that. And we now have our individual images. And then we need to move this file from this Docling Scratch folder into our static files Nginx server. Now, unfortunately, there isn't any move node that you can use for local files. So what we're going to do is just use an execute command. So just type in command, and this allows you to run a shell command. And we're not going to do this once. We want this to run for every file. Now, if you don't know CLI commands, again, you can just ask cursor. Essentially, it's NV for move. So we want to move this file. And now we need to get the path of this file as well. So again, back to cursor, you can see it's under shared, Docling Scratch. And also this is under data because it's the same as the trigger. This is all set in the Docker Compose. So here, when we have a local file trigger, we're looking under data shared. So it's the same here. And that's because the bind mount is against data shared, not shared. Okay, so we're going to move this file, data shared, Docling Scratch, and that's the file name. And now let's move it into our extracted images, data shared, extracted images. Okay, that should do it. So now let's run it. So execute workflow, and it has succeeded. And let's have a look at cursor. Let's refresh the file directory. Yeah, all of the images are now available under the extracted images folder. So now if we go to the browser, or if we go to our static files directory, we can see the images. And if we click into them, there's our whirlpool image, and we have the diagrams. Excellent. So this is probably the hardest part of this entire project, is actually to extract out the images and make them available to the AI agent. Excellent. So next up, we want to import this document into Quadrant so that we can actually carry out a vector search over it. So we can see the markdown content here. So actually, let's split off at this point, because this idea of moving the images can be done in parallel, essentially. So let's add a new node. Let's look for a quadrant. So there's our quadrant vector store, and we're going to add documents to the vector store. Now there is a local quadrant database already pre-configured in the N8N starter kit. So actually, let's just edit that. It's not working as well. So I don't think you need an API key. Let's delete it. And then back to quadrant URL. This is the same thing that we talked about here. So we need to reference this as the service name. And actually, this is the exact host that we need to hit. So let's use that. So there's quadrant URL. And actually, if we just click save, yep, it has succeeded. So yeah, for local AI implementations, there is usually no API keys required. Now, of course, you could set API keys if you wanted to lock it down within your network. Now, we don't have a collection yet. So let's go into quadrant. So back to Docker, there's quadrant, which is this one. And then for quadrant, it's /dashboard. Okay, so this is the quadrant vector store. So if we click on collections, we can add a new collection, and we'll call this one multimodal RAG. And continue. So then it's asking what's the use case. We're just using global search here, really. There's no per user documentation or anything like that at this point. And for this, we'll just use single dense vector embeddings. You could use hybrid search if you wanted. Okay, so we need to choose dimensions. We have a few options here. We want to use a local embedding model. And the one I typically use is Nomic Embed Text. So this is available on Ollama. And if you go to the Nomic website, you can see the number of dimensions that are in this embedding model. So you can specify for version 1.5. We'll go for the highest number of dimensions to get the best quality embeddings. So we'll just drop 768 in there. And then we're going to use cosine similarity as our algorithm to figure out what are the closest vectors. So we'll click continue on that. So we'll just click finish. Okay, so we now have our quadrant vector store or collection essentially set up. So then if we come back into N8N, we should be able to choose it now. So let me just save that and go back in. There we go, multimodal RAG. And there shouldn't be anything else to set there. So then for the embedding model, we now need to choose Nomic Text Embed. So we need to use Ollama. And again, we need to specify a credential to Ollama. So just click on edit, and it's looking for localhost, which again doesn't make sense here because we need to use the service name of the service within the Docker network. So that should be Ollama. And again, no API key, we can delete it. And if we click retry, yeah, we have a green message. So let's just save that. And it should load the models. Again, it didn't immediately. So let's just get out and go back in. And there we go. So this only has Llama 3.2. So we need our Nomic Text Embed model within our Ollama system. So if we go back to Ollama, you can see that there is a command we can use, Ollama pull Nomic Embed Text. So let's copy that out. And if you go to exec, what you can do here is you can execute commands within this container. So if I right click and paste it in, this is going to pull the Nomic Embed Text model into this container. And there is a volume mounted for Ollama so that when we destroy this container and recreate it, we won't need to import Nomic Embed Text again. So we'll trigger that. And now, as you can see, it is downloading this model. Okay, so that is successful. So now if we come back to N8N, back into embeddings, and there you go, Nomic Embed Text latest. So let's click on that and we'll save. And then the document, we need to attach a document parser or a document loader. So there we go, there's that one. I generally don't use the simple one. I prefer to use custom. So we'll hit custom. We'll add a recursive character text splitter. And I usually specify markdown as the split code. So that way it's going to retain some of the structure at least of the document in terms of the chunks it creates. And we might just reduce the chunk size a little bit. So maybe to 700. Okay, we are in good shape here. So now let's connect this up. Let's just remove this for a second because we just want to see how the vector store side of it works. And let's execute the workflow again. Okay, so that has injected into the quadrant vector store. And if you come into quadrant and click collections, yeah, you can see there's now 19 points within the vector store. Yeah, you can see all of the various embeddings. So there's the image URL. That's the table for kind of model sizes, product dimensions, etc. There is some nice visualizations within quadrants. So if you click on visualize and just hit run over the limit, it'll actually show you where the points are and how they are clustered. So it doesn't really mean much just with one document, but as you load more in, you can see how they are clustered. There also is a graph as well, which is kind of neat. And if you double click it, then it loads up other points close by. Cool, so we have our vector store. We have the data in the vector store. So now come back into N8N. Let's just hook that back up again. And now let's create an AI agent that we can actually converse with. So let's click on plus. We'll add a chat trigger, and then let's add an AI agent, which is that one. And now we need to add a model. So again, we're going to use Ollama. It has to run fully locally. It has specified the local Ollama service, and it has selected Llama 3.2, which is imported by default with this N8N self-hosted AI system. So we'll just save that. Now, that's a very small model. You're not going to get huge amounts of intelligence from it, but it might just be enough to be able to demonstrate this. So then in terms of a tool, let's choose Quadrant, which is our vector store. It has already specified the credential. Description-wise, we'll just say, use this to fetch information from the knowledge base, and then we'll just choose our collection, and let's limit it to 5. Okay, so we'll save that. We need our embedding model. Let's grab that from here. So obviously it has to be the same, otherwise you're not comparing like with like. And I think we're in business here. We might just set a very simple system prompt. I'll just say you must use the Quadrant vector store to retrieve information. Actually, a good tip as a starting point is if you add the prompt from this question and answer chain. So if you open it up and then just look at the system prompt template, that's not a bad starting point. It basically says, don't make things up. Yeah, let's use that instead. Okay, so now let's ask it a question. Maybe show me the cabinet opening diagram. Let's try. And actually, I need to add one more thing to the system prompt, which is you must output images in Markdown format using the URL provided in the retrieved results. Let's try that, for example. Okay, so show me the cabinet opening diagram. Let's see how it goes. Okay, it has triggered the Quadrant vector store. Okay, and we do have a response. There is no image that I can see anyway. Now that might be down to the size of the model, and it's not exactly ideal for instruction following if it's too small. Let me retry that again. Okay, there is images this time. The images are broken links though, so let's have a quick look at that. So let's just right click and inspect them. Of course, yeah, we haven't added the full path into the vector store. So let's close that out for a second and let's go back to our ingestion flow. And we essentially need to inject the full URL here. Now, these image paths are actually way longer than what the Llama 3.2 produced. So I'd say we need to upgrade the model anyway, but we definitely need to add in the full path. So let's add another code node here. And then same again. So I'm just going to copy this out and let's bring it into Claude, to Opus. I'll just create a new chat. It's always good to keep opening new chats in Cursor because as chats kind of continue on and on and on, the actual quality of response deteriorates due to kind of context rot and a few other things. Please create JS code that injects the full URL of images into the output MD content. Okay, so this is my input. This is an example of the full URL. So this is now my Nginx file server. So that's it there. So localhost 8080 essentially. And then again, let's drop in our JS skeleton here. Okay, so let's let it run. It's probably just a regex to find the image and inject in the URL. A bit of pattern matching. And here we go. So let's copy that out, drop it in here, execute step. And there we go. Yeah, HTTP localhost, and that's the full image. And let's just copy that into the browser to see did it work. Excellent. Okay, let's delete everything now from Quadrant and let's re-import the file. So within Quadrant, you can go through and delete everything. This gets pretty tedious. So let's hit this endpoint to delete the Quadrant collection and recreate it. That we can quickly kind of prune all of the vectors without having to manually create a collection every single time. So this is the endpoint. So let's add another HTTP request node. So what is this? This is a delete method. You pass that in, you pass in the collection name, which is multimodal RAG. That refused the connection, of course, localhost, so that needs to be Quadrant. Okay, so it deleted it. And if we refresh, no collection present. Obviously very destructive, so only to be used when actually building out your system. Okay, so let's copy that. So now this one is create collection. So we're going to post, I assume. We'll create a collection. That looks right. And then this is the body that we need to pass. So copy that out, drop it in there. And then what was it again? 768. Execute step. Didn't work. Oh, it's a put, not a post. So there we go. Brilliant. Okay, so we have it up and running again. Okay, let's actually run this fully now. So let's come back to Cursor. Let's just delete out the images that are there. Okay, so that's now gone to Docling. It's going to extract the images again. So if I refresh, yep, they've just appeared. And refresh, 19 points, perfect. And if we look through the vectors, we can see that this one has the full URL now. So now let's ask the same question to this agent and let's see, can we get a better answer? I feel like we probably can't. I don't think the model is big enough to be able to output the full URL reliably anyway. Oh, it did actually. There you go. Cool. All right, multimodal RAG, there you go. And using a very small model actually. So that's Llama 3.2, which is a 3 billion parameter model that's installed here. I'm quite impressed actually that it was able to spit out that image URL and actually call the vector store, because my experience of very small language models is that they can't even reliably call tools. But again, I'm sure if I ran this exact query 10 times, it might struggle to produce the image accurately 10 times. And that's really where you need probably a bigger model to be a little bit more reliable. I have no memory assigned here as well, so every time I refresh this, it's a fresh call. But yeah, it worked again there. Excellent. Yeah, that's great. As I mentioned earlier, if you don't have the graphics card to hand right now, you could hook up an open source model in the cloud to actually get all of this stuff up and running. So let's try that. So I'll come back into Ollama chat model. Let's create a new credential. And now let's just choose ollama.com. And if we go to ollama.com, if you create an account and go to API keys, you can create a new API key. So this is tutorial. Generate the key and we can copy it. And then if you paste it in here and click save, you'll get your green success message. And now the model list is a lot bigger because you're going to be using a cloud model. So let's use the GPT OSS 20 billion parameter model, which is of the right size that you could run on an RTX 4090. So we'll save that. And again, let's ask the same question. Now we've got unauthorized. Of course, I didn't pass the API key. No, I did. Now maybe I need to hit HTTPS. Let's try that and refresh. Oh, okay, that's actually worked for me now. All I did was created a new API key and it worked. I'm not exactly sure why it worked, but it seemed to work. So now we can choose GPT OSS 20 billion. And yeah, we can ask a question and we get an answer back. So, okay, let's hook up these tools again. Okay, we'll clear down the chat. So let's ask, show me the cabinet opening diagram. And yeah, GPT OSS 20 billion is lightning fast on Ollama Cloud. And there we go, we do get the cabinet diagram. So let's test it out with another PDF. So let's unpin this local file trigger and we'll execute the workflow. So now it's listening for new files in this folder. So let's ingest this document. This is 112 pages of a user manual. So that's still waiting. So let's drop this into our pending folder. And actually, we still need to move the completed file to the process folder. So that's something we need to do. But let's drop this in first. Okay, and that's hit the Docling API. This is where async would actually make a lot more sense because this is a rather large PDF. So that's something that we could implement again. And I can hear the fan spin on the machine here because even with the standard pipeline, there still is AI models. Okay, that has finished. Took 46 seconds for 112 pages. That's pretty decent, I think. And now it's working through the embedding process and it's moving 269 images into this Nginx file server. And yeah, there are all the images. So now let's ask a question. Show me how to use the ice and water dispenser. Okay, so we are getting instructions. Yeah, we're getting images. That's great. Very nice. GPT OSS 20 billion has such a tendency to output tables like that, which doesn't really work in a kind of a chat interface. It might just be some system prompting to try to force it not to do that. Just whatever way the model was trained. But yeah, you can see that we are getting images now through, which is great. Ollama Cloud only has a certain number of open source models. Let's try Open Router just to be able to get a flavor of the different models and the output formats. And again, this is all fine as we're testing and trying to figure out what's the best model for the job. Once we figure this out, we can download that specific model and then build the hardware to meet the requirements of running that model. Okay, so there's Open Router. And yeah, let's try Quinn. Quinn 3, 32 billion. Let's try that. Okay, we are getting images as well. No tables, which is great. Yeah, that looks pretty decent, actually. I'm happy with that. That's a great way to test and play around with lots of different open source models to figure out what's the best for your use case. So off camera, I was just testing different configurations of Docling and adding additional features. I created an async polling loop. So now here with the Docling local VLM pipeline, I'm hitting the async endpoint, and then I'm going through a polling loop where I wait for a set number of seconds, 3 seconds there. I check the task status using the task ID, and then based on the status of the task, when it's successful, we fetch the result and then we process it. Otherwise, if it's still processing, we go back and check again. or if there's an error, we can stop an error out here. I'm also moving the file now into the processed folder. So we have the full file path and then dropping it into RAG files processed. So that way then we can keep the pending folder clear. And once we activate the workflow, anything that's dropped into that folder will be consumed into the pipeline. And then some of the other configurations of Docling. So I had the Docling standard pipeline, and I was also playing around with the picture description API. So it's possible to annotate the images that are in the actual document itself. And you can specify how big the images are to actually be sent, because obviously you don't want to be sending really small images to the VLM. But it's cool that you can run the VLM alongside the standard pipeline where you're only actually sending in, let's say, diagrams and images. Now, a lot of the smaller VLMs aren't really suited to describe what's in an image. They're more specialized on actually figuring out what's in a document. So again, some playing around with the different models. I was trying Granite 3.2 Vision there, and I wasn't getting amazing results for kind of general purpose images, but I don't think that's what it's designed for. So yeah, you can see how you can kind of further build out this pipeline to accommodate the files that you're trying to ingest. And with enough effort, you can build out quite a complex and sophisticated RAG ingestion pipeline. So this is our local RAG system that we have available in our community. And within this system, we're looping through files that are dropped into a local file folder, similar to what we've gone through today. And then there's lots of different tracks for different file types. Because obviously Docling can handle lots of different file types, so that is a little bit of a catch-all. But for structured data like Excel sheets or CSV sheets, we want to represent those differently. And then once it gets into the main part of processing the files, it works its way through a record manager. We have knowledge graphs. We handle the tabular data, as I mentioned. And then we have lots of functionality around context expansion, extracting out document hierarchies, and then using contextual vector embeddings. If you'd like to get access to our state-of-the-art local RAG system, then check out the link in the description to our community, the AI Automators. So now that we have a version 1 of our RAG system up and running, let's create a web page where people can actually chat to the agent on the local network. Now we could vibe code a chat interface, but just to keep things simple, I'm just going to embed the standard N8N chat widget. So I'm just going to grab the URL for this, and let's come back into Cursor. Let's create a new chat, and let's just explain what we're looking for. And actually, let's just use this extracted images folder because the root of our Nginx file server is essentially this folder. So here we're going to ask, within this document root, can you create a web page that embeds the following chat widget? And then I want this to hit our N8N Docker container. And let's see what it does. Okay, so it's creating the web page. I'll create a beautiful web page with the N8N chat widget embedded. Okay, let's see how beautiful this is going to be. Now, I have got very good results from Claude Opus 4.5 over the last couple of weeks, so I do have high expectations. So let's have a look. Okay, N8N chat, your AI system powered by N8N. Click the chat bubble in the bottom right corner to start a conversation. Start chatting, and let's ask hello. Now, nothing's happening. I haven't even activated the workflow, so that's not a surprise. So let's come into the workflow, make chat publicly available, yes. I'll give it this chat URL, and I've set it as embedded chat. Don't need any authentication because it's local. So let's copy that and let's save it, and let's activate the workflow. And now let's just come back in here. The workflow is active. Here's the URL. Drop in N8N instead of localhost. It should probably figure that out itself. Okay, so let's try it again. Refresh that. Okay, we are hitting the workflow, which is great, even though it's an error. Now let's come back in here, executions, debug in editor. Yeah, I just need to make a change. Just need to update my credential. That looks good. Now let's ask it to show me how to use the ice and water dispenser just to see can we get images back. And as you can see, we've got through our response. The formatting is all over the place. I would not define as beautiful Claude Opus or Cursor. So definitely some iterations needed on the styling of this pop-up. And this should probably be embedded full screen. So obviously lots of work needed on the UI, but you get the idea that you can use this N8N chat embed and literally embed it in a HTML page, connect it to N8N, which is in a different Docker container, and away you go. So the last thing that's needed then is if you hit, let's say, localhost 8080, you're just getting this index of files, and then chat.html is just one of them. So let's come back into Cursor, create a new chat. And I'll just ask, can you adjust the Nginx configuration so that if someone hits the root for the static file service, that it's bringing them to the chat.html. And this is where Cursor is brilliant for making changes to the likes of Docker Compose files, because if you're not an expert at this stuff, it really can shorten the amount of time it takes to make these changes. And it was a pretty easy change, just index chat.html. Okay, so we just need to take down our static files container and then re-up it, and then that should be it. Okay, so let's test it out. Brilliant. So now localhost 8080 is pointing to chat.html, and we should still be able to access the images that are stored on that file server. So the last thing that's needed then is for users to be able to access this chat interface if they're on the local network. And there's not a huge amount of changes that are needed here if it's a small local network. So here, for example, this is my computer, this is my server, and let's say this is my local IP address. And let's say that we have other computers or other laptops that are on this network that want to access this chat widget. So when we hit this chat widget, we're hitting it at localhost 8080 or 127.0.0.1. And you can only do that if you're on your own machine. So if someone from a different machine was trying to access this, they would need to hit the actual local IP address of my machine on the network. And to hit this static files container, which now actually contains the chat interface, they would hit that IP address at port 8080. And if they wanted to access N8N, you could make that available at port 5678 as well. So to set this up, there are a few changes you would need to make. So by default, inbound connections to arbitrary ports like that are disabled by the Windows firewall in my case. So I would need to make changes to my firewall to allow connections in. This IP address that I have on this local network is essentially dynamic. So if I turn off my laptop and turn it back on again, I'll most likely be assigned a different IP address. So you may need to set up a static IP address so that the actual address doesn't change. There might be other network configuration changes you need to make depending on how complex your actual network is. And the bigger your organization, the more likely that there's going to be a lot more layers and a lot more systems in place. So you'll probably need to work with your comms team on that. And then the other obvious thing is your server needs to always be on, or at least on during office hours if you want people to access this chatbot during office hours. So that's how you can publish and effectively deploy your AI agent in your organization.
I'm using the agent mode in Cursor here to make some front-end changes to the local RAG agent. So I've embedded the chatbot fully on screen. And it's currently now iterating through the actual styles. This agent mode with the actual browser built in, and then the fact that it uses Puppeteer to actually simulate browser actions is really powerful for iterating on front ends like this.
And of course, this is a very basic multimodal RAG agent. I've just imported a couple of files here. But on our channel, I've shown lots of different advanced techniques that you can use to really build out the capabilities of a RAG agent like this. Now that you know how to create a fully local multimodal RAG agent, I highly recommend you check out this video here, where I show you how to deploy a clone of Notebook LM locally. Thanks for watching, and I'll see you in the next one.